Hi there, I'm Vanessa Sockett. I'm a computer scientist at Lawrence Livermore National Laboratory, and today we're going to be talking about trends and practices for pulling HPC containers in cloud. Let's get started. So, the story that I'm going to tell you today begins on an adventure that I took to California, a road trip last year. And during this trip, I had many things on my mind: life, work, people. But I also had something else on my mind. You see, I am a huge proponent advocate for containerization, and currently I'm very much into Kubernetes. My team is running a lot of workloads there, and we're doing a lot of development in the space. Now, like many of you listening right now, your first experience with containers probably goes back to the magic of Docker, when you can have many things running on your computer, or you shelled into another world and it felt like magic. My particular experience, I also started with Docker, but I also started as one of the initial Singularity container developers, which was kind of one of the first container technologies for HPC. I moved into developing Singularity Hub, which is what it sounds like. It was a registry for Singularity containers. I maintained it for 5 years while there wasn't a solution in the ecosystem. And then thanks to OCI, the Open Container Initiative, you could push the CIF as a single layer to a traditional OCI registry. Didn't need to host that anymore. And so the question on my mind during this time when I wasn't supposed to be thinking about work is, what is the best way to pull a container? Because this is something we do in cloud, we do it on HPC too, we do it all the time. And I had never really asked myself this. And so this was the foundation for a lot of the work that followed this particular trip. So what are we going to be talking about today? The first thing we're going to do is look at how the container ecosystem has changed since 2014. This is really important to understand different patterns of change to help us kind of predict what's going to happen in best practices. The next question is about those best practices. What do those changes mean for best practices? And then finally, can I simulate kind of the pulling part of a container study and build a tool that others can use to also simulate that? So that's kind of the container pulling part. And then once we understand that, can we step back and say, okay, now what are best practices for these pulling strategies? How do they hold up in different scenarios? And of course, the most important question, why should I care? It's very easy to dive into interesting technical work without really stepping back and asking this question. So let's start with, how has the container ecosystem changed since 2014? The first thing I wanted to look at is the stuff that I can get from registries. So the size of the entire container, the size of layers, the number of layers, image similarity. If you're familiar with OCI and you're familiar with registries, when you pull a container from a registry, you get back a manifest. The manifest is a JSON blob that has layers in it, each of which has an actual size and other metadata. So I needed a database. So there's a database called the Research Software Database. It has a curated research software from almost 6,000, I believe, at the time of the study repositories, but it's automated, it updates itself, so that number is larger now. And then I combined that with a set of machine learning GitHub organizations. From that, I was able to derive a set of 77,000 Docker files, each of which has a base image. So I need to make a distinction here that we have now the Docker files that are from the scientific repositories. Each of those Docker files has a base image that we can actually locate in a registry. So both of those pieces of information are going to be very important for the work we're going to do. Now we're going to use that registry, as I mentioned, to get those image manifests that have layers and sizes and lots of good metadata tidbits. And from that, we basically have two things. So from our base images, we're going to be able to ask questions and answer questions about layer and image sizes and counts. And then also from that data, but also from the Docker file images, we're going to be calculating similarity in various ways, because we really want to understand, is the redundancy being used here? How similar are our images? Okay, so let's start with a really easy question. The first question is, once we take all of those base images and we query the registry, how many tags does each one have? So very logically, this kind of reflects how often someone might have automation to build a container. But I'll note that the range is from 1 to 17,000, which means that there are some containers that someone just built and probably pushed just once and called it a day. But there's huge variations. So the mean was 1,842 tags with a standard deviation of 2,531. There was one outlier, NixOS, with 47,000 tags. And this depends on when the container went into the ecosystem, but this would be something along the lines of like 10-ish, assuming it's, about 10 years. I think this would be about 10 builds per day. But again, there's many variables there that would make that vary. And so as I mentioned, these tag counts really reflect build frequency. How often is someone's GitHub, CI doing the build for their community? And I imagine Nix is doing that pretty frequently. Okay, so how has the number of layers changed over time? This is a really kind of contentious topic in the sense that, like, some people might tell you, yes, you want to have fewer, more dense, meaty, compact layers that are, larger versus many, many tiny layers. And so first we can just kind of look at the data. And so again, the mean here we saw from 2014 up to last year was 16.58 plus or minus 23.66. Again, quite a bit of variation there. There are more outliers as the years progress. And here's the really interesting thing about this. So there's this common wisdom that thou cannot build more than an image with more than 127 layers. And actually, that's what's hard-coded as a check into the Docker command line tool. However, the actual limit has to do with a system call that basically makes the call, generates a string for mounts, and it's based on the length of that string that sets that limit. And so tools like Docker do an explicit check, and then they say, oh, nope, you can't build about this. But there's other tools like Containerd that allow you to do whatever you want. And if you hit a limit based on your operating system, based on your kernel, then that will kind of propagate up the error. But this was an interesting finding because it was an example of these common sources of kind of communal knowledge or wisdom that we have that oftentimes are wrong or oftentimes are right for a particular point in time, but not later in time when, a kernel changes or an operating system changes. So indeed, people are building and pushing to registries images with more than 127 layers. And actually for the paper, we tested this and we got well over 200. Okay, so how has the total image size changed over the years? So we take all those layers in the manifest and we add them up, the sum of the layers. So before, when we saw that the number of layers itself was pretty consistent, I would suspect people aren't thinking about this much. They're just like building their containers. The size, not surprisingly, also is getting larger. And this isn't surprising because, like, what are we building? We're building honkin' machine learning containers. Although it is kind of going down a little bit 2024, but it definitely is generally increasing. So, got to add in the meme, right? So in 2014, we had the popularity of the Slim Boy. And I need to point out, like, how many best practices articles and papers there were about, like, how to properly build your Docker container with multi-stage builds and making it super slim as possible. But when machine learning came around, man, all that is out the door. Containers in 2025 are like the super chunk, so it will be very interesting to see how this trend progresses. I would hope that if containers continue to get bigger with machine learning models and data, that we kind of go back and think about the implications of that and put into build tools or other strategies better ways to not have the costs incurred in something like pulling time, which we're going to talk about. And so just build smaller containers. The machine learning does not afford us to build smaller containers. I don't know if anyone's familiar with that. Okay, so TLDR, how has the container ecosystem changed since 2014? Our containers are getting larger, but the layer size is relatively constant. Alrighty, so now how similar are containers since 2014? Are we doing experiments responsibly and building them as similar as possible so we're pulling fewer layers? So the first kind of similarity, and I calculated a few kinds of similarity here, is the similarity of the scientific Docker files based on layers. And so here we're starting with 528,000 layers. And the logic here is to think of each layer in that Docker file, so that's actually a set of commands, like a document. We can tokenize that layer, and we can use word-to-vec embeddings, which by now is a very old algorithm, but it's one that I like a lot. And then we can use those embeddings, length 300, with cosine similarity to calculate this chart right here. And so what do you see? Well, you see that the values are very low. So the majority of the distribution is between 0 and 0.1. So yeah, layers are not very similar based on actually their content in that manner. Now, what if we look at the digest? So to step back, each layer has a content digest, and that's what determines if it needs to be pulled again. Because if you have two different images with the same digest, you can basically cache that. You don't have to pull it again. And the story is kind of the same. So the story is that, well, no, the layer digests are not very similar. So now an interesting question that I was personally curious about, what's the most commonly used base image? So this is harder than it appears at face value because I'm not just looking at the from statement. I have to figure out, often based on the file system, like pull the container down, look at the file system, figure out what operating system I have. So I actually use an algorithm that I previously published, it's provided by the GUT software. And I can share a paper in the notes of this video. But the basic idea is that we're going to take each of our contender images and we're going to compare it against a database of not just all of these operating systems, but different versions of the file system. And then we're going to do some tricks, again, in the algorithm, and we're going to calculate a similarity metric that's based on the similarity path using the Jaccard coefficient. We're going to get a score for each of these bases and versions against our contender operating system paths. And then we're going to assign the highest one as the classification. And so these scores, just to quickly show you, they tend to be very high. And from the other paper that I published, the prediction tends to be very good. So the result, anyway, is that the most highly used image is Debian, followed by Alpine, and then Ubuntu. I wasn't surprised about that. My go-to tends to be Debian and Ubuntu, and then Alpine is kind of like for the special small applications, maybe like a Go binary and a multi-stage build. Okay, so how does a container building strategy, so when you do an experiment and you go about building your containers, how does that impact the ultimate similarity in the sense that, like, is there a way to build containers so that container layers are more similar so you don't have to do as much pulling? So the first thing that I kind of need to note is that more similar containers means more redundancy of layers, less space in the file system, again, super chunk, or like, oh Lord, he's coming, oh Lord, here he comes. So there's going to be three kinds of kind of real world sets of Docker containers that I use to assess or actually look at this question. The first is a reasonable effort to create redundancy. So my team did a real performance study across 3 clouds. We built hundreds of containers, but we made a solid effort to make them as similar as possible in the sense that we wanted as many layers at the onset similar, so then maybe only the application code at the end would be different. And this is because we were paying for the study and we wanted to minimize the cost of pulling. Now, for the next set of containers in the study, I took that initial set and I further optimized them based on best practices. And, in the case that there was one layer that was off and it made a container slightly less similar, I basically fixed that. So this was taking a reasonable effort and really making a solid best effort. And the third one represents a set of containers with little effort to create redundancy. So SPAC has a tool so SPAC is a package manager. SPAC has a command called containerize that generates a multi-stage build that will install whatever packages you want in an environment. However, the design of that is that it builds them all into one really big chunky layer. Again, the super chunk. And so there's so little chance that you would ever have redundancy of this layer because everything in SPAC is very niche. So this would represent, at least from the point of this study, little effort to create redundancy. So let's first look at the containers from the real performance study. And I want to show this to you because it really reflects how containers kind of match their environment. So here is clustered similarity from that study. I believe this is the Jaccard coefficient. And the really cool thing about this is that the different sections in this plot represent different environments. So on the top left, we have AWS and Google GPU containers, then the CPU containers. Then we have Rocky bases for compute engine because that was suggested as a best practice, Azure GPU, Azure CPU, and then kind of the brown regions are obviously dissimilar containers between environments. And then there's a few brown regions that are kind of in the corners, and those are like a couple of SPAC containers that we built for a couple of applications. So now let's look at a slice of that set. So what I did is I took a slice of that set, a smaller set that I wanted to use for this particular study. So here we have our three building strategies. We have the real performance study containers. We then have the best effort of the same containers. So notice that the similarity scores go up. And then we have SPAC on the right. And so there's a table in the bottom, and this is more in the paper, but kind of the takeaway point here is that when we look at unique pulls that would be required for each build strategy, when you make a reasonable effort, 45% of layers are unique. So again, that's about half of the layers that need to have their own pull because they're not like any other layers. When you make an effort, only 28% of them are unique. So that's much better. And then with SPAC, because there's largely no redundancy, probably just that base image layer, a huge 89% of layers are unique. So what we know, what we kind of knew, but I wanted to empirically see, is that redundancy of layers increases similarity. So what about best practices? How are people in the community doing with respect to best practices? The first question we have is about multi-stage builds. So you've probably seen a multi-stage build. You'll see two froms in the same Docker file. And it's because in that first stage, you'll build your software, you'll compile, and then you'll want to get rid of all the build assets because all you really need is that binary and then the runtime dependencies. So you copy some kind of special, the binary from the build, and then you add it to maybe a slimmer container and you get a much smaller container in the end. So this was easy to derive from our data. We looked in the Docker file database, looked for more than one from in a Docker file, and we found that about 2.56% of image builds use a multi-build strategy. That's more than I expected, but over the entire set, it's still pretty tiny. The next thing we looked at are people using Docker official images? So this is one of those things that I'm not really sure if it actually is a best practice or if it's a best practice because Docker Hub says it's a best practice. And this was easy to do because we could look at the from directive and parse the registry and see if it's docker.io. This was surprising to me because almost 15% of image bases actually were from Docker Hub. But, as one of the major contender registries, maybe I shouldn't be so surprised. Okay, latest tag. So if you've been on the reproducibility train for over 10 years now, no, it hasn't been that long. Yes, it has been that long. It is usually considered bad practice to use the latest tag because it's like a moving target. When you pull latest today, latest next year is going to be like a different operating system and your entire thing is not going to work. So you usually don't want to do this. So again, we can look at the from directive. And this was actually really good. Only 5.3% of images used a latest tag. Not too shabby. Good job, community. Now, are people using pinned image digest? So if you imagine like the dimension of reproducibility, there's like the latest tag, like YOLO, like I'm gonna get something, I don't know what it is. And then there's like a pinned digest, like I'm only gonna get this exact one. And then probably a version is somewhere in the middle. So this does guarantee an exact build, but the trade-off is that you may lose, for example, like security updates. So I think a more reasonable approach is actually to choose a version tag, which typically will get security updates and that kind of thing. So in order to find this, we needed to look at the SHA-256 for a SHA-256 instead of a tag. And this is a very uncommon practice. This is less than 1% of entries in our database. Okay, so the next is apt-get and install in the same line. And this is actually a very good suggestion because when you combine get and install, and then especially when you add clean, you're cleaning up the layer so that it doesn't have a huge number of extra files, because even if you run it in the later layer, they're still going to be in the previous layer. So it's really important that you do the clean when you're executing commands in that layer. So I found 507,695 layers that use apt-get. Of that set, 94.3% also have an apt-get install. So most of these are doing install of software. And guess what? A really large percentage, 67.8%, do a clean too. The community is doing amazingly on this tip. I mean, this was a great find. However, it does not matter. So this makes such a big difference that this particular thing to do a clean is actually built into the tools. So if you were to actually do an apt-get install, and you didn't do the clean, the tool is going to clean up the layer for you. And this is code from that I found at the time when I made this talk. It's of course subject to change, but this is a really good example of, tool developers knowing that something's a really good practice and putting it into the software so the users don't have to think about it. But very ironically, the users in this case very much have thought about it and have done a really good job. So great job actually to both users and developers in this case. Okay, so TLDR, people don't always follow best practices, but really what we think is best is that the tooling implements them so we don't have to. That's my opinion, to be frank. Okay, so what's more important, image size or number of layers? This goes back to that, having people tell me like, oh, more layers, fewer layers, bigger layers, smaller layers, like what does it really matter? Does it matter at all? Well, if it's cake, it absolutely does matter. But what about for containers? So I had this question, and I built a simulation tool called Container Crafter specifically for polling studies. And the basic idea is that you start with this configuration file, and you say, okay, I want to test across all of these sizes, and then I want to test either these exact number of layers or this range of layers. And then the tool will actually build all those containers to a specific URI. Each layer is only allowed up to the registry limit, which is 10 gigabytes. And I want to note that the values that I selected here come directly from the Docker file database. So these are actually percentiles from the images that are representative of what people have been doing, except for the last three in the range where I added more because they get much larger. Specifically, I believe that goes up to 19 gigabytes. So yes, here we go. What I just said, but here's the entire human readable table of all of the sizes and the percentiles that I used. So does the number of layers matter? No, it absolutely does not. So what you're looking at here is a number of layers on the x-axis and then the pull time in seconds on y. And then there's 4 sizes on the right side. And actually, I think I have plots with more sizes I'll show you. But what we see is that only for the largest size, which is the 19 gigabyte container, you actually see pull time shoot up to anything that would be significant or that we cared about. For all the other sizes, which to be fair are smaller, much smaller, everything is flat on the bottom. So to be clear, if you look at, for example, the largest container, it doesn't matter if you have 1 layer, so all the way on the left, or you have 100 layers all the way on the right, the time doesn't really change that much. So yeah, the number of layers doesn't matter. And guess what? So I ran this study because I was saying like, oh, what should I use in my follow-up experiments? But when I really thought about it, would I have really chosen some artificial value that looked a little better? No, I really think the best choice would be to choose what people in the community are actually doing. So for the follow-up study, I chose the median of this data set, so 9. And then I chose the max, 125 layers, to see if there was any sort of bounding behavior. So what's more important? Image size is more important. Probably a lot of you could have said that, but already. Okay, so now let's get into the meat of the study. What is the best strategy for container polling? Now, I designed a cloud polling study. It would be run on Google Kubernetes Engine or GKE. I would use a fairly small instance with 16 vCPU, so that's 8 actual cores, 60 gigabytes RAM per node. I want to note that I also tested on a larger instance, so that was 64 vCPU, and the additional performance was small relative to the additional cost, which was much larger, and I decided not to use that. We're going to be testing quite a range of cluster sizes from the smallest size 4 up to 256 nodes. Now, for each container size and layers, we're going to create a Kubernetes job to pull the container, and we're going to use the Kubernetes and exporter to collect events. And there in the right, in the blue box, you can see that the performance was barely better, but it was 3.87 times more expensive. So yeah, that was a no-brainer in terms of choosing if I wanted to use it or not. And then each experiment will be conducted several times to assess some particular setup. So what setups are we talking about, you say? Well, here are some strategies that I found for optimized container pulling in Kubernetes. And actually, this is one of the first things that I started to read about when I came back. Actually, no, I started to read about this on my trip because I clearly have no self-control. So the first one is to use a cloud-provided registry. So the idea here is saying that, like, well, if you're using a registry that lives alongside the cloud, then the containers that you're pulling are like physically closer. So there's going to be, less network latency because of that. The next one is to use a solid state drive instead of a persistent disk. And then the third is to use something called image streaming. I had no idea what this was at the time, but there's an open source tool called the Soshi Snapshotter we'll talk about that kind of implements that sort of algorithm. Now, the next two are things that I didn't wind up looking into, but they would improve pulling time. So the first is to use a different compression algorithm, such as standard compression. It would be greater than 3 times faster than gzip. The problem here is this would take a lot of customization of actually your container runtime and various tools. And I wasn't convinced that this is something that someone would actually want to do or figure out how to do before they did a study on, a public Kubernetes cluster. So I decided it wasn't reasonable. The other thing you can do is preload images onto your nodes using a daemon set. And that does make sense, but it also, would require a lot of kind of thinking ahead. And I wasn't also convinced that people would be building nodes that are similar enough that it would really be worth it in the end. So for my study, I wound up looking at specifically these 3 approaches because I thought these would be the most simple for the user and the most reasonable thing to do. It's not to say that the other ones do not have feet or do not deserve future time and research. I just decided not to choose them. Okay, so I was going to do 2 kinds of tests. First, with containers generated from the simulation tool, which are simulated containers, so they don't have a real application in them. And then I was going to use real-world application containers. And I was going to make it really hard. I was going to use those containers that were built with Spec. And I also, something I thought of while I was working on this, is that I wanted to test node coordination. Because you can imagine that it doesn't matter how good your pulling strategy is, if you need all the nodes in the same state in order for your application to start across nodes, if you have one slow node that slows that all down, you're really waiting for the slowest node. So that is actually an important detail. Okay, so let's look at the results of the pulling study. Does pulling from a local registry improve in pull times? I was pretty surprised about this. The answer is no. So here we are looking at pull times from GitHub Container Registry ghcr.io. We can compare that with gcr.io. Yeah, the interesting thing is that when I first looked at this, I was like, oh, there's more variability, for example, in the size 4 cluster. But then you look at the larger sizes, and actually it goes down, and it seems like it either seems random or not a really consistent pattern. The other thing that really surprised me, which you might see right off the bat, is that the pull time doesn't increase for larger clusters. And actually here in this particular result, for the largest container, so that's the one on the right, that's about 19 gigabytes, the slowest size was actually the smallest cluster. So there's no kind of, I did not see any pattern or association there. Now here they are overlaid, and again you can see that when you statistically compare the means, they're not significantly different. The distributions are very much overlapping. Now, does pulling with a local SSD solid state drive improve times? Absolutely, often 1.25 times. So here we see, at this point, we're using gcr.io because I chose one. And we can see the before. So here's actually the before. So here's gcr.io without a special file system. And when you add it, it goes down. And so these are very cheap. And so just right off the bat, if you have, no time to think about things, add on a local SSD, and you're going to save, you're going to have a little bit of savings. Okay. Now, does pulling with image streaming improve pull times? When I first saw this plot, I was very perplexed. So what you're looking at is basically that on the total image size on the x-axis and the pull time. Across sizes, for cluster sizes 8 until 256, the pull time is like a second. I mean, it's like instant. The interesting thing is that it was only the size 4 node cluster. So actually, let me walk through this with you. These down here, the pull time is instant. The reason that is instant is due to image streaming, but it's not explicitly that algorithm. There's actually something else combined here. You see, with the size 4 cluster, this was the first time that Google Cloud had seen me trying to pull these containers. So you'll notice that the actual pull time did get a lot faster. So it's 17.5 seconds is a lot faster than times we were seeing before. So the snapshotter, basically, that we're going to talk about next, that is working to make the amount of content that needs to be present before you start the container a lot less, so it's faster. But the other thing that Google Cloud is doing with image streaming is it's actually caching your images, not just within a cluster, but across clusters. So by the time that I got to a size 8 cluster, it didn't matter because Google was going to be using my images that were cached from the size 4. I thought that was excellent. And I totally didn't expect it. It was a surprise, but that's a really nice design decision on the part of Google. So I did the same test again with real application containers that would actually have to run something and prove that they were loading, different content from these big chunky spec containers. So this is combined applications for AMG, LAMPS, OSU, and Mini FE. And we see the same pattern. The size 4, they'll take longer, so between 35 and 40 seconds. But then after size 4, it basically swoops down to immediate. The entire image is cached. And this is compared to when you don't have image streaming. So that's sort of the aqua boxes, where every time you do have to do the pull. So these aren't huge containers, so it's not like a crazy unreasonable pull time, but you can see the savings here. Okay, so let's talk, now you're probably wondering, what the heck is image streaming? Why are we looking at it in the first place? So to go to way back, why did the initial kind of developers investigate it in the first place? They noticed that image download accounts for 76% of container startup time. Because what's basically happening is that container D might be running on your node or your HPC system, and container D basically needs to get that manifest and then take the layers in a particular order, extract them into a snapshot, kind of freeze the snapshot, and then keep adding layers until it's done, and then it prepares the final image for you to use. And so you could wait for the whole thing. That's actually kind of like the native strategy. But what they found is that only 6.4% of data is actually needed for the container to start doing useful work. So it's like, could there be a way to maybe just download like the stuff that we need to start and then do an on-demand lazy loading strategy? So this was way back in 2016. Now, I'll give you the kind of the caveat here that I did a 45-minute talk on the intimate details of SOCI, the Seekable OCI snapshotter, the StarGZ snapshotter, down to the code, down to the calls, and all of this. This talk is already pretty long, and I am not going to go into that level of detail today. However, if you're interested, watch this talk, and this is really funny because I'm wearing like almost the same outfit. Well, minus a few things. I don't have many different fashion choices. So let's talk about high level how this works. So what happens with a snapshotting tool like this is first that you actually are going to be recording your application entry point. When you do that, you're recording the first 15 seconds and you're looking at the file system and you're figuring out what files are basically touched or read or interacted with in that first 15 seconds. This creates a set of prioritized files that are highlighted here in yellow. Then we set a landmark that says, okay, stop fetching here. So what this is going to tell container D is that when you get to this point, you can actually stop there and then move the container forward, and it can transition from pulling to actually ready to run. And so, of course, if you don't have this, then there's a no prefetch landmark, and there's a few more details in here. So the way that this works, of course, is that, the thing that you're looking at here is called a table of contents. And so this table of contents is kind of what it sounds like, and it needs to be put somewhere, right? So it needs to be put somewhere, and that the place it's put is actually alongside the image in a registry. And this is possible thanks to the OCI artifact. So again, this is explained in more detail in the other talk, but the basic idea is that the connection happens by way of when you ask for a particular container, you first get back manifest list, okay, which platform do I want? Then you get a specific image manifest. That specific image manifest will point to a refers manifest. A refers manifest has different artifacts in it. So you've probably heard of SBOM, software bill of materials. The Soci index, that table of contents that we just looked at, that is one of those artifact blobs. So basically then you can get the index, you can get the artifact. The artifact has basically an entry for all of these different files, so that container D that's running with this snapshot or enabled can pull the image, can pull the table of contents and be like, okay, these are the exact files that I need for startup. But then what happens though after startup? What happens when you start your container and you make a call to ask for some file that wasn't loaded? So let's talk about that. So let's walk through these steps. So a snapshot, as I mentioned, is a view of the container file system that's prepared from a layer. So we need to start from a registry that supports artifacts. So that means the pushed image and associated table of contents. So for Google Cloud, this means that for image streaming, you're required to use the registry. And actually, this is another really cool design by Google, because they've designed it so that when you push your container, it actually will generate those table of contents for you. Now, they're probably not using Soci, but the Soci that derives from StarGZ derived originally from a project that was created by Google. So there's probably some similarity in the algorithms and code so we can make that comparison. So the snapshotter plugin knows how to get the table of contents, knows how to get the image. It's just going to download the prioritized files, prepare the image. The image is going to be running. From the standpoint of the user, it just starts running really quickly. And you're like, wow, this is total magic. Now, after those prioritized files are downloaded, the container is ready, et cetera, et cetera. Okay, so here's this question. How does additional content get loaded on demand? And this is actually a very simple answer. It's using something that the distribution spec calls resumable pull. And the basic idea is that because in a registry, everything is stored as a blob, and because we have that index that says, like, here is the exact location in the blob of this file, we can use custom fused file systems that when they ask for a particular file, we basically just query the registry to get the exact location of the blob, this resumable pull, and we download exactly what we need. So yes, we already talked about that. And underlying all of that is just a really simple HTTP technology, a range request, where you ask for just a range of data. So that's really cool. But what are the caveats? So the caveats are that if you have an application that needs a lot of really large data later in execution, you have to be very cautious, because this can actually, because you're downloading the data when you need it, this can actually lead to performance detriments for the application itself. So this is a time where you really need to think about, okay, do my containers afford a strategy like this? Or will I be better off doing something else to pull them onto the machines, or just using a solid state drive, right? Alrighty, so this was kind of the conclusion that I came to after going into the most wonderful of rabbit holes and learning about these snapshotters. And I definitely recommend you watch the other talk if you're interested. But yes, solid state drive is a really good idea always. It's super cheap. Image streaming, maybe sometimes. And it's definitely an interesting space for developers to think about and continue working in. So now let's talk about that node coordination bit. How well are our nodes wearing their cute little matching outfits? So does node coordination lead to slower pull times? Are we limited by the slowest node? So something really interesting happened in my study. I saw that despite the fact that pull times didn't increase across my sizes, the overall experiment time increased with cluster size. So like, how could that be? My entire experiment was bringing up the cluster, which which was pretty consistent with Google Cloud. It usually comes up in like 550 to 600 seconds, and then bringing it down, and then pulling the containers, and then bring it down. That was the entire experiment. There weren't different applications in here that would have different run times, at least not that was another part of the study. So where is this extra overhead coming up so that, as you can see, as the number of nodes increases, the total experiment runtime does as well? I think it has to do with node coordination. And so let me give you just one example. So this is just the pulled event across nodes. And this is showing you broken apart by different colors for image sizes. So the aqua color is that really large container. And what you're looking at is the biggest time difference between two nodes in the cluster. So for our largest container, we see that time difference goes up to 50 seconds. And so if a time of 0 would mean that all of the nodes do this particular action at the same time, a time of 50 seconds means that there's that much kind of stagger between them. And so when you think about this, and this needs some further follow-up, this would be way too much to put in one paper, but Kubernetes has so many different events that are going on. We know that the scheduler is processing a single queue of pods with an index job. It processes batches of those single pods. So I think what happens is that we're actually getting this inserted kind of overhead when our clusters get bigger. And what we really need to do is better understand all of the events, where the overhead is coming from, and if there's ways to improve it. Because if we want to run really large studies in a cloud, we don't want the overhead to increase like that. That's a lot of time when you're not really doing anything different. And because the pulling time doesn't increase when you add more nodes. Each node is doing its own thing. Alrighty, so node coordination. Nodes are less coordinated as nodes increase. We don't really know why. We have some hypotheses about events, but this needs further work. So now the most important question, the takeaways from the study. Why should I care? So what did I learn from this work? So the first obvious thing is that a container building strategy that's optimized for similarity in container layers, especially when you're doing stuff with GPU containers that are large and using expensive resources, and a polling strategy, which can be a file system or an algorithm or something else that I didn't test, to decrease pull time can decrease total cost for a study. And we're going to look at an example for that. This improvement becomes especially salient when you're using expensive resources such as GPU or an auto-scaling strategies, because with auto-scaling, you're going to have new nodes added to the cluster that don't have any container images cached. And you're going to have to pull them again. So that's problematic, right? And then if you're running an application, all your other nodes are going to be waiting for those nodes. So yeah, all these things. Now let's walk through an actual, thought exercise, because I did this and I was like, yes, obviously I might save a few minutes. Do I care about that? Should I care about that? So here's my thought exercise. Let's assume we have 10 applications. I chose this because this reflects what we did for a performance study. And let's just take the means. So I took the mean layer size, 12 MBs, the mean number of layers, 16. So for the study, we use the median. This is the mean. And I said, okay, let me create this hypothetical set of applications. Now, how can I think about this? I decided to look at these extremes. So on the far left extreme, the most ideal case where you have perfect redundancy and you only have to pull all the layers for all your 10 applications once, and then they're cached, and then you're good to go. That's kind of the left extreme. In the worst extreme, you have no redundancy, no shared base images. That means you have to pull 16 layers each time. So how many pulls? How many licks does it take to get to the center of a Tootsie Pop? How many layer pulls does it take to get to your container? Okay, I need to point out that the best hypothetical case doesn't make sense at all, because you would essentially be pulling only one unique container. But we have 10 containers, but just imagine this is a gradient here. So it's, that's the hypothetical, not realistic extreme. In that case, we'd only be pulling 16 layers. In the worst case, we'd be pulling 10 times that, so 160 layers. So how much stuff is that? In the best case, under these hypothetical scenarios and assumptions, we'd be pulling 192 MBs. In the worst case, add a 0, so 1,920 MBs. Now, what does that mean for pulling time? So I looked up what is sort of like the average rate for pulling from like Docker Hub, and it gave me this rate of 3.5 MBs per second. Now, arguably this, again, these are the assumptions that I'm making. Probably if you use a specific cloud that has a much better network setup, this could be faster. But under these conditions, in the best case, the 192 MBs will be pulled in 39 to 64 seconds. Not bad. I have many memories of pulling containers, and that seems like a very reasonable thing. In the worst case, it can take 6.4 to 11 minutes. So we subtract those two, and the differences in our decision for how we built our containers comes down to an additional 5.75 to 9.6 minutes. So now the question is like, okay, what does that actually mean in terms of money? So for this hypothetical scenario, I imagined that I would be using a node type that actually my team might be using very soon, the P5 48 extra large. That is $98.32 per hour on demand. I will note that if you get a capacity block, it goes down. So for a size 32 cluster, which was also actually the largest size in our experiment study, which is approximately $3,146 per hour, that would be an additional cost of $300 to $500. So I looked at that number and I thought about it, and I realized that I do care. And the reason that I do care is because I believe this is like experimental hygiene. As researchers with limited amounts of funding that we are responsible for, I believe it is our responsibility to make our best effort to not waste money. And it's not just the wasted money or time, it's the fact that when we're using those resources to pull containers, someone else doesn't get to use them. And guess what? Given the resource contention for resources like GPU in the cloud, this is a pretty big deal. Now, this was also very salient to me because I had just the past weekend done about $300 of work on a cloud with GPUs, and I made amazing progress. And so what I thought about is like the opportunity cost of that much work that I was able to do if I'm just kind of careless about how I build my containers in a couple hundred, that is worth it to me. Now, let me give you actually, though, the more realistic case, because this is kind of small beans. What if we don't look at like the Docker file database, and what if we take a representative container that's actually a large machine learning image? So I went back to my thought exercise, and I said, you know what? Let's imagine now we have 10 images like PyTorch. Nothing else. So no customization, no data set, just PyTorch. So there's actually, I believe, 5 layers, but there's only 3 of them that are very large. And so that's the ones that you're looking at here: 30 MBs, 7.3 MBs, and 3.6 gigabytes, which I'm guessing is the base layer. So imagine now that our study has 10 images like this. Now for sizes, again, in the best case, we're just pulling 3 layers. So we're just pulling the sum of those values. In the worst case, well, we're doing that times 10, which is a very big number, 36.593 gigabytes. But how big? Well, let me show you. Okay, so again, assuming 3.5 MBs pulling time per second, in the best case, is going to take 12 to 20 minutes. Not a huge deal. Okay, it's probably going to be expensive on a GPU cluster, but like I can imagine 10 minutes of pulling over a study would be like a few minutes here, a few minutes there, like that's fine. But in the worst case, it's going to take 122 to 203 minutes. So again, we subtract those two because we have to pull our containers, in some way. And the difference is 110 to 183 minutes. Now, here's where it gets kind of like alarming and astronomical, and oh my God, this is absolutely important. We go back to now this setup, same instance types, about $100 per hour. The size of our cluster, like the experiments, if they took an hour, would be $3,146 an hour. But guess what? Just pulling containers would add, based on our strategy, would add an additional $5,768 to almost $10,000. So more time here pulling containers than the entire study. Now, of course, this is an extreme. The network would probably be faster. You probably wouldn't be pulling 10 size containers that are unique, that are the size of PyTorch. But this really tells you that minimally, folks, we need to have awareness about this. We need to cost estimate before we go into these experimental studies. Okay, so some additional strategies, because in many of these cases, image streaming doesn't make sense if you're not going to stream like a huge machine learning data set. So I will just quickly show you, if you're using a setup like parallel cluster or any kind of thing with like a login node where that auto scales that has a shared file system, you can bring up that tiny node, pull all your containers first, and then have your workers bind to it and use it. And actually, this is what we did with parallel cluster, and we use singularity containers. Now, if you're using auto scaling, you can, in sort of a cloud environment, you can do something similar, but use a setup that mounts some kind of volume that, again, has those containers that are pre-pulled. This is sort of like the daemon set, although it's putting them just in one place, so you're not waiting for them to pull across many nodes. You can use a pull-through cache, so that the basic idea of that is it's a service that you deploy that when you pull a container, it pulls through it. So that caches your containers. So then when other nodes in your cluster need the container, it's actually already kind of pulled from the registry, the initial registry. And guess what? For innovation, we can explore other algorithms for predicting content to pull, compression, and file system latency. For example, image streaming would be really cool if you added a component of machine learning in there that could actually start pulling what you need with enough time in advance so that by the time you get to actually needing it, you don't have any kind of latency or performance detriment. Moving on in what did we learn from this work? This was actually one of the more interesting findings. Extra time is accumulated as the cluster gets larger. We think it has to do with node coordination. We need to further look into this. To do. Finally, I believe that container streaming really is an ideal strategy for quickly starting containers that are large, but caution should be used if large amounts of new data are needed for application execution later. And of course, this depends on the cloud too. So if you use Google Cloud and it's going to cache your entire container across different clusters, absolutely use image streaming. But if you deploy the Sochi Snapshotter, for example, in AWS, well, it may not have that same cache, so you may need to do something else. Now, let me quickly share some really interesting findings. There's more. Okay, so I found the Genghis Khan of container layers. So there was an outlier digest in this set. It appeared almost 68,000 times. And it turns out it was an empty set of 32 bytes. Yes, an empty set of 32 bytes associated with a working directory directive. However, it was only for cases when the directory already existed. So if you think about it, this is a layer that's totally empty and that it's doing nothing because you're not actually creating a new directory. If you don't know, normally when you do work directory, it doesn't just set a working directory. If that directory doesn't exist, it creates it. So if you created the directory, you'd actually have new content there. But you can also do work directory when something already exists and then essentially like nothing happens. So it turns out there's this empty layer flag in the image config. And if a tool decides not to set that flag for some reason, because it needs to still ship a valid tar gzip, even without anything being there, it basically needs to generate this digest. And so this thing takes up space in the various headers, but it's like, it's nothing, it's empty. And actually this was implemented before it was discovered that dev null is actually a valid empty file. And so this is an example of what you will find in the wild if you search for this digest. It is all across different tools. I think it's been removed from a lot since now, but I think this is in nerdctl. It's still hiding out there in the wild. Genghis Khan having his influence in this digest. Okay, so the next really interesting thing, I kind of alluded to this a little bit, is just this common wisdom. So I started with an understanding the container, layer limit is 127. Thou shalt not go above 127. I never asked why. I probably should have. In Docker source code, though, you actually find references to different numbers depending on the overlay. And again, Docker is really like enforcing it. They aren't going to let your computer error out and then propagate the error up. They're just not going to let you go over that. But containerd doesn't set a maximum. Containerd will absolutely let it go down to your kernel, and this is call, and then throw up an error. So this was actually really fun. I brought this to the OCI Slack, and we were talking about this. So Tianan, that probably many folks in the container community know, just took the empirical test, like, let's just build as many layers as we can. And the largest that we got to kind of put to build and then push to registry was 256 layers. I think the one with 400 might have failed, but this was really cool. Okay, so I actually already talked about these things. I didn't mean that. But the interesting thing about Docker is that it will fail on it's still, even though it like checks for you, it still fails on the mount step after pulling the layers. So you'll be waiting like 6 minutes or something to pull your layers, and then it like do that. I can't do this, and to go back to a really good movie. Again, this is information you could have told me before pulling the container. Ah! So I hope from this talk you feel like you have a little bit of superpowers when it comes to pulling containers. You're minimally a little better informed about strategies for building, strategies for pulling, and maybe you're even a little excited about the space of work to be done, looking at new algorithms and methods and this node coordination issue. If you're interested in Soshi, I found that the way that AWS had me install it was hard. So I made a daemon set installer that's applying one YAML file, so you can try it out very easily. And on that note, that's all I got. I hope you enjoyed the talk today. I am probably going to go off for a run and do other dinosaur things. If you have any questions, please don't hesitate to reach out. I love working in this space. I love the community. Thank you to everyone for making it such a wonderful career. Take care.